So in this video, we're going to be talking about complex numbers. So we're going to start off with a definition. First thing we should do is just define what an imaginary number is. So let's say I or j is the imaginary number such that I squared is equal to -1. So that's the main property that we want to think about related to this imaginary number. Now you're free to use I or j, whatever symbol you're most common with or you're most commonly used to. In engineering, pretty common to use j. In math, pretty common to use I. I'm going to stick with I just because that's consistent with the course pack, but as I mentioned, feel free to use either. They're interchangeable. Okay, so that's what an imaginary number is. I squared is equal to -1. And then from there, we want to define a complex number. So if we write something like z equal a plus bi, then we say that's a complex number. And in this context, a and b are real numbers. So what makes z a complex number is that it has a real part and an imaginary part being added together. So those are our first two definitions, and based on that we're going to do a bit of algebra. So let's say, for example, we've got two complex numbers. So in that situation we'd likely call them z1 and z2, just like that. Let's say z1 is -2 plus 6i, and let's say that z2 is equal to 4 plus 5i. So in this example, we just want to make sure that we can do things like scalar multiply, add, subtract, and multiply two complex numbers. So let's see how to do all of that. So part A, if we had to calculate something like -7 times z1, then what we do is multiply both the real and the imaginary part by -7. So we'd have 14 minus 42i. So that's what scalar multiplication of a complex number looks like. Part B, let's try adding these two complex numbers together. So z1 plus z2, we're going to add the real parts together. So -2 plus 4 would give us +2. And then just add the imaginary parts together. So 6i plus 5i gives us 11i. Altogether, 2 plus 11i. Great, so let's do the same thing with subtraction. We are going to subtract the real parts now, so -2 minus 4 gives us -6, and then 6i minus 5i gives us 1i, or just more naturally I. So -6 plus I is what we get there. Okay, final part here, part D. Let's do that up here. We're going to see how to multiply z1 and z2 together. So let's take -2 plus 6i, multiply that by 4 plus 5i, and the idea here, just FOIL it out. The main property we need to remember, anytime we see an I squared, we're just going to write that as -1, or just imagine that as -1. So -2 times 4 is -8. Continuing to FOIL this out, we'd have -10i plus 24i, and then you'd have 6i times 5i. You could call that 30i squared, or better just to call that -30. So then final touch here, let's just add the real parts together. -38 plus 14i. Great, so that's how we scalar multiply, add, subtract, and multiply complex numbers. Now we want to work towards seeing how to divide one complex number by another, and to do that we need a definition. So we're going to talk about the complex conjugate. The complex conjugate of a complex number. Let's say z is equal to a plus bi. Complex conjugate is written z bar, and what it represents is the complex number a minus bi. So if we say this intuitively, what a complex conjugate is, you're just taking your original complex number and you're changing the sign of the imaginary part. The real part stays the same. Let's do an example. Let's say z equals a plus bi. And we are going to show that if we take z and we multiply it by its complex conjugate, that we end up with a squared plus b squared. Okay, so that's our goal in this example. All right, so to show that, let's start with z times its complex conjugate. So just by the way we've defined these things, we've said z is a plus bi, and then by definition, the complex conjugate of z is a minus bi. So let's try foiling this out and just see what we get. So we'd have a squared minus abi plus abi. And then for the last terms here, we'd have minus b squared times I squared. Remember, every time you see an I squared, that's really like -1. So this becomes plus b squared. And so what happens here is these second and third terms cancel, and sure enough, we end up with a squared plus b squared, which is exactly what we were trying to show. Okay, so now we're going to use this fact to see how we can divide complex numbers. Let's take two complex numbers. We're going to call them z1 and z2. Say z1 is 4 plus 9i. And let's say z2 is minus 3 plus 5i. So what we want to do in this example is find z1 over z2. So we'll figure out how to make sense of this division process. All right, so to start the calculation, z1 over z2, let's just write out the details. We'd have 4 plus 9i over -3 plus 5i. And the main trick to dividing complex numbers, the trick is we are going to multiply top and bottom by something. And so by multiplying top and bottom by the same thing, we won't be changing the complex number, we'll just be changing how it looks. Trick is to multiply by the conjugate of the denominator. So let's take the denominator, change the sign of the imaginary part, so that becomes -3 minus 5i. So that's the conjugate of the denominator. And whatever we do to the bottom, we got to do that same thing to the top. So there we go, multiplying. And see, the magic that's going to happen here is in the denominator. We saw in our previous example that if you take any complex number, you multiply it by its conjugate, you're going to get a squared plus b squared. So we already know, without doing too much thinking, what this denominator is going to come out to. It's going to be the square of -3 plus the square of 5. So without doing really much calculation at all, we know this number here is going to be 34. And that's what the secret to dividing complex numbers. All right, so let's FOIL out the top. We'd have -12 minus 20i minus 27i. And then when we get to our last terms, you could call that minus 45i squared. But because I squared is -1, we're just going to say plus 45. Okay, so then finishing touches here, the real parts would be 33, and the imaginary part minus 47i. Okay, so 33 minus 47i over 34. That would be okay in terms of a final answer, but I would say it's a little better to distribute that denominator so that you're really separating the real and the imaginary part. So 33 over 34 is the real part, and then minus 47 over 34i is the imaginary part. That's our final answer, and that's in general how you divide one complex number by another. So next idea we're going to look at here, we're going to make a connection between complex numbers and vectors. There's a reason why we're doing complex numbers within the framework of linear algebra. So let's just come up with a definition here. We're going to define the length, or sometimes called the modulus, either way, length or modulus, of a complex number. Say specifically our complex number is z equal a plus bi. And so we're going to define this length or modulus in terms of notation. We'll write z with vertical bars around it. It looks like an absolute value, but it's not properly speaking an absolute value. It's just the length of our complex number. And the way that we actually calculate the length is we say it's the square root of a squared plus b squared. So we'll draw a picture in a minute and just to understand geometrically why that would be the right thing to do. Second thing we're going to talk about is angle. So we're going to define the principal argument. Principal argument, really just a fancy way of saying angle. So again, let's say we're talking about the complex number z equal a plus bi. And we're going to define notation for the principal argument. We'll call it theta, since really what it is an angle. And the way we're going to calculate it, arctan of b over a. And then in brackets here, I'm going to write plus pi question mark. So whenever you're using arctan, the arctan function to determine an angle, you always have to be a little careful about the quadrant. And so my plus pi question mark here is just a way of reminding us to be careful about the quadrant. We'll look in detail through an example what exactly that means. Okay, and then just for consistency, we assume that this angle is going to be between negative pi and pi. So it could be equal to pi, would be strictly bigger than negative pi. That is just so that we all come up with the same angle, so that we don't have a situation where one person's saying 3 pi and another person's saying pi. We've got a standard way of defining what the coterminal angle is. Okay, so that's the definition behind length and angles associated with complex numbers, and I think this will become more clear if we just draw a picture. So let's say, for example, we've got the complex number z equal -1 plus 2i. So we can visualize this complex number in the following way. So we let the horizontal axis represent the real part of an imaginary number, and we let the vertical axis represent the imaginary part of a complex number. If we do that, then we can actually graph complex numbers. Our real part is -1, imaginary part 2i, so we're going 2 units in the imaginary direction, and that takes us over to here. So our complex number can be associated with a vector in this plane here. Okay, now if we think about our new definitions just geometrically, then when we say length, we're just talking the length of the vector. So the length, or the modulus of z, just our usual formula for length, we're going to go square root of a squared plus b squared. So that would be root 5 is how long that vector is. And then let's talk about the angle. So the angle, or formally the principal argument, we are going to go arctan of, you're taking your imaginary coefficient over your real coefficient. So 2 over -1. And the way the arctan function works, it will return the correct angle anytime your angle is on the right side of this diagram. So if you're in quadrant 4, quadrant 1, arctan will give you the correct answer. But if you're in quadrant 2 or quadrant 3, arctan will give you the wrong answer. And the correct way to get the correct angle is to add pi. So if you're in the wrong quadrant, if you're over on the left side of the diagram and your angle's actually in quadrant 2 or quadrant 3, adding pi is always the right thing to do. Okay, if you wanted to put this into radians, about 2.03 rads for our angle. So that's how we associate length and angle with complex numbers. So in this example, we're going to show that any complex number z is equal to the length of z times cos theta plus I sine theta, where the length and the angle are exactly as we defined just a couple minutes ago. So to show this, let's picture our complex number as a vector like we did in our previous example. So imagine you've got any complex number, let's say for example, complex number looks like that when represented as a vector. So you can talk about the length of z, and it might be helpful to label our axes here. So there's our imaginary axis, there's our real axis. Okay, so now let's figure out the principal argument associated with this complex number, so that's the angle theta. And let's imagine trying to resolve this vector here. Let's actually label it. So this vector is the complex number, and associated with that vector we've got a length and an angle. Okay, let's try to resolve that vector into components. So if we did that, let's draw a picture. Have a right triangle. We know this is angle theta. We know the length, that the hypotenuse is the length of z. So resolving into components, this would be the length of z times cos theta. And then your vertical component would be length of z times sine theta. All right, so since we know that our complex number has its real part represented along the horizontal axis, we can say, well, that means the real part is going to be length of z times cos theta. And since we know that our imaginary component is going to be represented vertically, then we can say the imaginary part is going to be plus length of z sine theta times I. Okay. And then a more natural way to write that, you would factor out the length of z. And this also becomes more readable if you write the I in front of the sine theta. So you'd write cos theta plus I sine theta in these square brackets here. So that's another way of thinking about complex numbers. Now let's give some names to the two different ways that we've come up with so far for writing these complex numbers. We've written z equal a plus bi. That's what we started with. And then just now we've shown that z can also be thought of as the length of z times cos theta plus I sine theta. So we basically want names for these two different notations. So the top one is called rectangular form, and the bottom one here is called polar form. Express the complex number z, which looks like -1 plus 8i. Let's express that in polar form. So in order to do this, we're going to need to think about calculating the length of z, think about calculating the angle associated with z, and then we'll put that all together into the proper polar form. All right, so length of z, excuse me, as we said before, square root of a squared plus b squared. Okay, so if we take -1, square it, plus 8 squared, that gives us 65. So in other words, our length is root 65. And then we need to think about the angle. So theta is going to be arctan of b over a, where we're talking imaginary coefficient over the real coefficient. And then I like to just get in the habit of saying plus pi question mark. If our complex number is actually in quadrant 2 or quadrant 3 when we graph it, then we will need to add pi. All right, so we're going to have arctan of 8 over -1. If we want to figure out whether to correct quadrants, just make a very quick sketch here. So z has a negative real component, positive imaginary component. We know z is going roughly something like that. So that tells us, yeah, because we're on the left side of the diagram, we do need to add pi here. So perhaps cleaner way of writing this, you could write the pi first. Remember that arctan is an odd function, so if you have a negative inside the arctan, you'd more naturally write that as minus arctan of a positive, and we could just say that minus arctan of 8. So pi minus arctan of 8 would be a better way of expressing that angle. So now, just remembering what our polar form looks like. In general, polar form says to write your complex number as the length of z times cos theta plus I sine theta. We figured out that the length of z is root 65, and then we're just going to sub our angle, which we figured out, into this expression. So we need to write something like cos of pi minus arctan of 8 plus I sine of that same angle and then close our square brackets. So just filling in this angle again, pi minus arctan of 8. So there we go, that's our polar form. So one of the reasons why polar form is useful is because it actually works out really well to multiply and divide in polar form. This fact is going to tell us how to multiply and divide quickly in polar form. So let's say that we have two complex numbers, and let's say that they're given to us in polar form. So we would write length of z1 times cos of, let's call the angle associated with z1 theta 1. So we'd have cos of theta 1 plus I sine theta 1. So that's representing z1 in polar form. And in a similar way, we'd write length of z2 times cos of theta 2 plus I sine of theta 2. All right, so let's see how to multiply first, and then we'll talk about division. So to multiply two complex numbers which are written in polar form, well, the new length is just going to be the product of the two lengths. So you're going to take length of z1 times length of z2. That's your new length. And then your new angle is going to be the sum of the two angles. So to express this in polar form, we need to have cos of whatever our new angle is plus I sine of whatever our new angle is. So let's just figure out what the structure is for how we're writing that. So that's the structure of polar form, and the angle that we're actually putting in here is the sum of the two angles. Theta 1 plus theta 2 is our new angle. So if you said this to yourself intuitively, you just say, well, when I multiply complex numbers together, the lengths multiply and the angles add. Now if we were to divide complex numbers, the lengths are going to divide. So we'd have length of z1 divided by length of z2. And then let's just write out the structure, what polar form looks like. So you're going to have cos of something plus I sine of something. And whatever the angle is going to go into these brackets. So what's going to happen with the angles is we're going to be subtracting them. So angle associated with the numerator minus angle associated with the denominator. So more briefly, when you divide complex numbers, the lengths are going to divide and the angles are going to subtract. So what we'd like to do here is we're going to find z1 over z2 by converting to polar. Let's say z1 is 9 plus 3 root 3 times I, and let's say that z2 is 4 root 3 minus 12 times I. So notice that we've got these two complex numbers. They're given to us in rectangular form. So our first job is going to be to convert them both over into polar form, giving us more practice with getting into polar. And then once they're both in polar, then we'll be able to use this fact that we just wrote down. All right, so let's start with z1. Let's think about the length of z1. So according to the definition for length, you're taking the square root of each of your coefficients squared and summed up. So you'd have 9 squared plus the imaginary coefficient is 3 root 3, so we need to square that. All right, so if we think about what we've got under the square root, that would be 81 plus 27. So in other words, 108 under the square root. So you could leave it like that, or if you wanted to simplify this, you might just happen to notice 36 divides into this. If you did notice that, you could write that as 6 root 3. Otherwise, you could just leave it as root 108. So let's figure out the angle associated with z1. That's going to be arctan of imaginary coefficient over the real one. So 3 root 3 over 9. We need to ask ourselves, do we need to add pi? And the answer is no, because if you were to graph this complex number z, you'd see, oh, well, the real part real part here is positive. That means Z is going up and to the right. It's on the right side of the diagram in any case, and so we don't need to do an angle correction, so that's nice. All right, so we're talking arctan of, this is going to simplify to 1 over root 3, or you could call that root 3 over 3 if you want inside the brackets. Either way, and that's one of our special angles. So arctan of 1 over root 3 is pi over 6. So what that does is allows us to rewrite Z1 in polar. So our length is 6 root 3, and polar form always has the form length times cos of our angle plus I sine of our angle. So 6 root 3 times cos of pi over 6 plus I sine pi over 6. Great, so let's do the same thing for Z2, perhaps a little bit faster. So length of Z2, maybe I'll just put this in a box because we're going to use it in a minute. So length of Z2, if we did that a little bit faster, let's talk about the length first. So it's going to be the square root of a squared plus b squared. So if you square the 4 root 3, 48, plus square of the imaginary coefficient, and that gives you root 192. Can leave it like that or call it 8 root 3, whatever you prefer. I just like to keep the numbers small. And then if we think about the angle for Z2, arctan of negative 12 over 4 root 3. Because the real part is positive, this vector is going to the right, don't need to correct the angle. So we could call that arctan of, let's just simplify the fraction here, minus 3 over root 3. So let's just say minus root 3 would be the best way of writing that number there. So that gives us an angle of minus pi over 3. Okay, so now with that, let's write our Z1 and Z2 in polar form. I think I'll do that on the next screen, and then we can easily see how to divide the two. Okay, so just copying from the previous screens that we've got everything. So we said that our length of Z1 was 6 root 3. We said that our angle was pi over 6. So cos pi over 6 plus I sine pi over 6. That's what we had on our previous screen. And we were just figuring out what Z2 looked like in polar form. So we did the work to figure out that the length of Z2 would be 8 root 3. And we figured out that the angle would be minus pi over 3. So if you wanted to write Z2 in polar form, you'd write 8 root 3 times cos of minus pi over 3 plus I sine minus pi over 3. So strictly speaking, not really necessary to fully write these out in polar form unless the question asked you to. Since we were asked to convert to polar form, we did all the details. But if you were just trying to find Z1 over Z2 quickly, really all you'd need to do is just think about the length. What is the length of Z1 over Z2 going to be? And what is the theta value going to be? So if you want to reference what you're doing, you could say, I'm trying to find the theta for Z1 over Z2. You could just write that in a subscript. Okay, so the length for Z1 over Z2 is just going to be the ratio of the two lengths. We'll take 6 root 3 over 8 root 3. If we simplify that, that's 3/4. So that's the length of Z1 over Z2. And if we want the angle associated with the complex number Z1 over Z2, we're just going to subtract the two angles. You need the angle of the denominator, or sorry, the angle of the numerator first. So Z1 on top, we're taking the angle of Z1, pi over 6, and then we're going to go minus the angle of whatever's in the denominator, so minus pi over 3. Okay, so double negative there. That's like 3 pi over 6. So pi over 2 would be a better way of saying that. So now for our final answer, what we're going to do is write down what Z1 over Z2 is. We've figured out that its length is 3/4. And let's write out polar form. So that's going to be times cos of the angle plus I sine of the angle. And we know what our angle is. It's pi over 2. So if someone told you, give your answer in polar form, then you'd say this. It wasn't specified in the question what form to leave our answer in. This might even be nicer, for this particular question, might even be nicer to go back to rectangular. Reason being that cos of pi over 2 is a pretty nice number, so is sine of pi over 2. Because we know cos of pi over 2 is equal to 0, because we know that sine of pi over 2 is equal to 1, we can really just say this whole expression just becomes 3/4 I. So in this question, you have flexibility about how to leave your answer. So that's how we multiply and divide in polar form. And this is one of the reasons why polar form is really useful to us. I'm going to look at something called de Moivre's formula. And this basically says if you've got a complex number written in polar form, then it's easy to figure out powers of your complex number. So let's say in this context, n is going to be a positive integer. So n equal 1, 2, 3, etc. To take powers of z, what we're going to do is we're going to exponentiate the length. So the appropriate exponent is going to go onto the length. And we're going to multiply the angle by n. So we'll have cos of n theta plus I sine of n theta. Again, that exponent they're referring, or that n they're referring to whatever number's on the exponent. Great, so if n is equal to 1, then this is just restating your polar form, but it's useful for n equal 2, 3, etc., larger integers, larger positive integers. So this actually follows from what we said before. We said that to multiply two complex numbers, you're multiplying their length and adding the angle. So if you now imagine multiplying a bunch of copies of z by itself, what you would expect is to have all those lengths multiply. So sure enough, you get length of z times length of z, however many times you're multiplying. And then the angles are just going to add. So you're going to have theta plus theta plus theta n times. In other words, n theta. So let's use de Moivre's formula here to do a calculation. Let's find 1 minus I raised to the power 21. And the idea would be not to multiply this by itself 21 times, but let's convert it to polar form, and then we can use de Moivre's formula pretty easily to get the answer. So just to introduce some notation, let's say z is equal to 1 minus I. I'm going to move into polar form by getting the length and the angle. So length of z is going to be root 2, and the angle is going to be arctan. We're taking imaginary coefficient over real coefficient, and we need to think about, do we need to add pi to this? Okay, so anytime the real component is positive, that tells you that your vector would be going over to the right. That means you don't need to correct your angle. So positive real component, don't need to correct the angle. Negative real component, do need to correct the angle. So in other words, theta is just equal to arctan of -1. So negative pi over 4 is our angle. So what that allows us to do is then write z in polar. So we can say z is root 2 times cos of minus pi over 4 plus I sine minus pi over 4. Great, and then here's de Moivre's formula coming up. So we're going to exponentiate this, z to the power 21. What are we supposed to do? Well, we're supposed to put that same exponent on the length. So root 2 now raised to the power 21. And what are we supposed to do to the angle? Well, multiply it by whatever our exponent is. So we get cos of now minus 21 pi over 4 plus I sine minus 21 pi over 4. Okay, so just to check here, our length has been raised to the correct exponent. Our angle has been multiplied by whatever that exponent was. Great, so this is technically our answer, but we would normally simplify this. We could rewrite this in either polar form or rectangular form, but let's simplify it and just see what we think is going to be better. So let's talk about the length and the angle separately. All right, so to make sense of this root 2 to the 21, let's think of that as root 2 to the 20 times another root 2. The reason why I do that is because if you raise root 2 to any even power, you're going to end up with an integer, because root 2 squared is going to be a nice number, root 2 to the 4th, etc. will be nice. So that simplifies to 1024 root 2. So that seems like a better way to think about that length there. And then for this one, let's find a coterminal angle that will make evaluating cos and sine a little bit easier. Okay, so we need to take our angle minus 21 pi over 4. We can add any multiple of 2 pi to this and end up with the coterminal angle. So just think about adding some various multiples on. If we add 2 pi onto here, we've still got a negative angle. Try adding 4 pi, 6 pi, etc. until you create a positive number. So 6 pi would work well. We want to add 6 pi. That's valid because that's a multiple of 2 pi, so that's going to give us a coterminal angle. But instead of calling that 6 pi, let's just call that 24 pi over 4 so that we can actually do the addition. So that gives us 3 pi over 4. And again, the reason why we're doing this is just so that then it's a little bit easier to evaluate cos of minus 21 pi over 4. So just doing a bit of a side calculation here, cos of minus 21 pi over 4 is going to be the same thing as cos of any coterminal angle. So cos of 3 pi over 4, and that's going to give us minus 1 over root 2. Sine of minus 21 pi over 4, same thing as sine of 3 pi over 4. 3 pi over 4 is a second quadrant angle. Sine's going to be positive there, so it's actually 1 over root 2 for the sine value. Okay, so all of that I would consider side work. Once we've got that worked out, then we can say z to the 21. Well, that angle, or that length there, rather, the length can be simplified as 1024 root 2. And let's say we wanted to write this in rectangular form. That's what we were sort of working towards here. So the cos of minus 21 pi over 4 becomes minus 1 over root 2 plus I times whatever sine of that angle is, so 1 over root 2. And the nice thing about this is that if you then multiply it out, see the root 2 in front of the brackets will nicely cancel with the root 2's in the denominator. So you'd actually have minus 1024 plus 1024i would be your answer in rectangular form. To me, that would be the most natural answer because the number was actually given in rectangular form. But if you wanted to give an answer in polar form, let's write it over here for the sake of space. So if you wanted an answer in polar form, your length best expressed as 1024 root 2. And it is nice to give the version of the angle that's somewhere between negative pi and pi. So it would be best to write cos of 3 pi over 4 plus I sine 3 pi over 4. So that would be if we wanted to give our answer in polar. That's just sort of an aside because I think rectangular here is really the best answer. So that's the end of that example. Now, if you are following along with the PDF file that I'm going to post alongside this, I just want to mention you can ignore pages 8 to 9 in the PDF file. So those pages actually have to do with calculating the nth roots of complex numbers. It is a nice topic. Some years we cover it, some years we don't. I consider it optional. I think this year not necessary to do it. So if you are interested, feel free to take a look, but I'm not going to explore that in the videos. So let's skip to what would be page 10 of the PDF file. And the next idea we're going to look at is just calculating powers of I. If we write I to the 0, well, just like with real numbers, if you take any real number to the 0 other than 0, any non-zero real number to the 0, you get 1. And it's the same with I. So I to the 0 is equal to 1. I to the 1 is equal to I squared, we know, is equal to -1. And so if you did something like I cubed, you'd think of I cubed as being I squared times I. So -1 times I would be -I. So I squared times I, you'd say -1 times I to get you -I. And then we could even do I to the 4th if you wanted. You could say I to the 4th is I squared times I squared. So that would be like taking -1 times -1. That would give you back to 1. Okay, well, this is better imagined with geometry. So let's imagine saying that I to the 0 is equal to 1. Let's draw that as a vector. So we could say I to the 0 is here. And then I to the 1 is I. So if we draw that as a vector, because our imaginary axis is up here, I to the 1 would be over here. Okay, then -I over here. So, or sorry, I squared is our next power. So what we're doing here is we're calculating the different powers of I, and then we're graphing them as vectors. So I squared is -1. If we visualize that as a vector, that's going to the left along the real axis, and then I cubed we said is -I, so that's going down along the imaginary axis. Okay, and then what's going to happen is the cycle is going to repeat. I to the 4th is equal to 1. I to the 5th, it turns out, is the same thing as I to the 1. I to the 6th, same thing as I squared, etc. So we just have this really nice geometric interpretation, which is that each time you multiply by the next power of I, you're really doing a rotation by 90 degrees. So you're going from this vector here, rotating 90 degrees, now you're here, then you're going over here, then you're going over here. So rotation by 90 degrees as we multiply by I. So for example, if we had to calculate I to the power 271, good way to approach this would be just to think about the multiple of 4 that is less than or equal to 271, the biggest multiple of 4 that is less than or equal to 271. So you could say, well, 271 is not a multiple of 4, but neither is 270, neither is 269. You could just work your way back like that, and you would figure out that 268 is actually a multiple of 4. Okay, so we could think of 271 as being 278 plus 3. In other words, you'd have, using your exponent rules, you'd say I to the 271 is I to the 268 times I cubed. That's a great thing to do because as soon as you've got a multiple of 4 in your exponent, you could say, well, then that I to the 268, if you wanted to be really formal about it, you could say that would be I to the 4th times whatever number you can put here to make your 268. So let's just think for a second. 268 divided by 4 is going to be 67. So then I to the 4th to the 67 is the same thing as I to the 268, but I to the 4th we said is 1. So I think when we say this, we're pretty much overthinking at this point, and we should just say, well, we know that I to the 268 is going to be 1 because we've already said geometrically that every time you get a multiple of 4 in the exponent, you're going to be back to where you started here. So I to the 0, I to the 4th, I to the 8th, I to the 12th, etc. are all going to equal 1. That's the slick way to do it. So you say this is 1 times I cubed, and then it would just be a matter of simplifying I cubed. Again, referencing our geometry, I cubed is better expressed as -I. So let's go back to our diagram here. I just want to really fix this up, clean this up, and then we'll come back to this example once we've figured everything out. So what we're saying bottom line is that I to the 0, I to the 4th, I to the 8th, etc., all of these better expressed as 1. That's the simplification. I to the 1, I to the 5th, etc., all better expressed as I. That's the simplified version. I squared, I to the 6th, etc., all of these better expressed as -1. And I cubed, I to the 7th, etc. All of these better expressed as -I. And so now let's jump down to our example. So I to the 268 times I cubed, if you're doing this the fast way, you'd say, well, I to the 268 is going to be 1, and I cubed is going to be -I. So 1 times -I. That way you've got a really fast way of computing any power of I, and the answer is always just going to come down to one of 4 things. It's either going to be 1, I, -1, or -I, depending where you are in this rotational pattern. So now that we've talked about powers of I, another example coming up. So we want to show that e to the I theta is equal to cos theta plus I sine theta. And we're going to be given some hints to help us along the way. These hints are going to involve some familiar power series from calculus. So let's just write a reminder here that sine x can be thought of as x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus, and so you've got an alternating series consisting of terms with odd exponents here. And then cos x starts with 1, contains a bunch of terms with even exponents, and it's also an alternating series. So it looks like 1 minus x squared over 2 factorial, so our signs are alternating here, plus x to the 4th over 4 factorial, and then you'd have minus, etc. So those are our power series for sine x, cos x, and we'll do the same thing for e to the x. So e to the x looks like 1 plus x squared over 2 factorial. All the coefficients are positive here. All the coefficients are 1 over the appropriate factorial. So 1 plus x squared over 2 factorial plus x cubed over 3 factorial, etc. So consider that all to be given, not something that you need to know off the top of your head in linear algebra. But we're going to use these facts together with the ideas that we just talked about around calculating powers of I really quickly. Turns out that if you put those two ideas together, then you can show pretty easily that e to the I theta is just another way of writing cos theta plus I sine theta. So let's try it. So let's start with the left side of what we're trying to show. We want to basically expand out this e to the I theta and show that we are getting cos theta plus I sine theta. Let's just replace the x in this formula here for e to the x. Replace that x with an I theta. So we would have 1 plus I theta all squared over 2 factorial plus I theta all cubed over 3 factorial plus ... Beautiful. Okay, now we're going to use our ideas about powers of I. We'll see how much we absorbed from the last example. So first two terms can just stay the same. This term here, we're going to call that I squared theta squared over 2 factorial. And that I squared, better expressed as -1. So let's just say minus theta squared over 2 factorial. Okay, then we get to our fourth term here, the cubed term. So I cubed theta cubed over 3 factorial. And then remember our discussion from before. I cubed better expressed as -I. So let's do that right now and just say this is minus I times theta cubed over 3 factorial. Okay, then we'd have our theta to the 4th term, etc. And the pattern of the coefficients, if you ignore the factorials for a second, the pattern of the coefficients is just going to go according to the powers of I. So it's going to be 1i minus 1 minus I, 1i minus 1 minus I, divided by the appropriate factorial. So let's see what that does for us. Let's continue our calculation of over on this side here. Let's just separate the real from the imaginary. So the real terms would be 1 minus theta squared over 2 factorial. If you continued this pattern, you'd have a plus theta to the fourth over 4 factorial. Maybe I'll write that down just for the sake of seeing that. So you'd have this alternating series here. Signs are alternating, and you've got your even powers. Okay, and then let's group together the imaginary terms, and since they're all imaginary, might as well factor the I out. So you'd have theta minus theta cubed over 3 factorial. And if you had been excited in our previous step and wrote out a few more terms, you'd see things like plus theta to the fifth over 5 factorial, and that's alternating, so then you'd have a minus term, etc. So alternating series in terms of our coefficients alternating sign, and you just have odd powers in this term. Okay, so now let's look back to the given information. This 1 minus theta squared over 2 factorial plus theta to the fourth over 4 factorial, that's nothing other than cos theta. And then we're going plus I times, well, this power series that's multiplied by I, that's nothing other than sine theta. So sure enough, yeah, we don't really need these brackets here. Sure enough, we're getting exactly cos theta plus I sine theta. What that does for us is it gives us a few different ways of writing down complex numbers. So there are actually 4 commonly used forms for a complex number. So let's just talk briefly about those. So the 4 forms. The rectangular form was our first one, where we said z equal a plus bi. Then we saw polar, where we said that's where you think about the length of your complex number and you think about your angle, and properly you write length of z times cos of theta plus I sine theta. And we've just now figured out that this stuff in the square brackets can be better expressed as e to the I theta. That's just going to give a faster way of writing this down. And when we use that, we usually call it exponential form. So you could equally well say z is equal to, we still have the length of z there, but instead of writing all this stuff in the square brackets, we just have an e to the I theta. So that's exponential form. Expresses exactly the same idea as the other 2 forms. It's just a different way of writing it. And then again, there's a 4th form, maybe familiar to some of you, maybe unfamiliar. It's called phasor form. And that's really closely related to exponential form. It's really just a slight notational difference where you write your length of z, and then you just describe, pen issue, and then you just describe the fact that you're going to give the angle here. You're describing the angle, so you write something like that, and then you just put your angle in there. So I would say that's very closely related to exponential form. You just don't write down the e and the I, but what you're doing is you're describing the length of your complex number and the angle. So really, I view polar form, exponential form, and phasor form, all of these very closely related, essentially just notational differences, whereas rectangular is equivalent, but is a different way of writing down your complex numbers. So 4 different ways of describing a complex number. We're really now getting into the last topic within complex numbers, and that is we want to talk about complex eigenvalues and eigenvectors. So we're going to do this just via one example. Let's take a 2 by 2 matrix A. Say it looks like 3 minus 13, 5, and 1. And the problem is going to be to find a basis for each eigenspace. So that's going to involve finding the eigenvectors of this matrix, it's going to turn out that they're complex eigenvalues, which is why we're doing that within this section. And then once we've got those eigenvalues, we'll just figure out how to find the eigenvectors. So this is going to give us a little bit more practice with complex number algebra. It's going to give us a little bit more practice with eigenvalues and eigenvectors as well. So let's talk eigenvalues. The way we do that is we set the determinant of a minus lambda I equal to 0. So let's take the determinant of the following matrix. We're going to subtract lambda from the diagonal entries, and the off-diagonal entries are just going to stay the same. We're going to set that determinant equal to 0. Okay, so doing our usual determinant calculation, multiply along the main diagonal, and then subtract off the product of the backwards diagonal and say that's equal to 0. So let's just expand this out. We'd have 3 minus 4 lambda, if we collect the outer and inner terms, plus a lambda squared, and then we'd have plus 65 equals 0. So in other words, lambda squared minus 4 lambda plus 68 equals 0. So most of the time in the examples we've seen so far, this polynomial, or this equation, rather the polynomial in the equation has factored nicely. Unfortunately, not the case here. So we're going to think about using the quadratic formula. We'd say lambda equals negative b plus or minus the square root of b squared minus 4ac all over 2a, and let's see what's what here. So negative b is going to become a positive 4 plus or minus square root. Under the square root, we're going to have the square of negative 4, so that's 16, minus 4 times 68 times 1. So if we work that all out, that's minus 256 under the square root. Okay, and then dividing by double the leading coefficient, which is 2. So let's think about just cleaning up this root here. Usually what I do is I just cross that off and I think, okay, that's the same thing as root 256 times root negative 1. And then from there we can even express that a little bit better, because root 256 is 16 and root negative 1 is, of course, I. So what we end up with here is just a 16i. And so that's telling us that our lambda values then are 4 plus or minus 16i, because that was just that root that we simplified, and that's all over 2. So dividing both terms here by 2, 2 plus or minus 8i. So those are our eigenvalues. First and only example that we'll see of complex eigenvalues. So very last thing we're going to do then for this topic is just practice finding eigenvectors in a situation where we have complex eigenvalues. Let's try it. All right, so let's look first at lambda equal 2 plus 8i. Specifically what we're going to do here, we're going to find a basis for the eigenspace for 2 plus 8i. So let's think about how to do that. In general, when you go about finding eigenvectors for a matrix, you're going to go A minus your lambda times I, and we are solving a homogeneous system. So let's go back to our matrix. The entries were 3 minus 13, 5, and 1. I'm just double checking that from our previous screen to make sure that I had written that down properly. Okay, and then subtracting 2 plus 8i from just the diagonal entries. So both the 2 and the 8i need to be subtracted here, so we'll do that simplification in the next step. All right, so diagonal entries are now going to be 1 minus 8i and minus 1 minus 8i. Off diagonals will stay the same, and we got our zeros here. So what we want to do is get this into our REFs so that we can solve the system, and this is going to be much easier if we swap rows, because if we swap rows, then we've got a real number in the upper left. That's definitely going to make life easier. Okay, and then from there we can divide by 5. So rho 1 over 5 is going to give us 1 minus 1 minus 8i over 5 with the 0, and the bottom row won't be changing at this point, so just our 1 minus 8i and our minus 13. Okay, and then last step, to get this into our REF, we have to take row 2, and we need to subtract off 1 minus 8i times our new row 1. So let me recopy the top row here. Okay, so row 2 minus 1 minus 8i times row 1, that's going to give us a 0. And then we're going to focus in on this entry here. So I'm going to show you fast way and slow way of doing this. Fast way of doing this, really, we know that this is going to be 0. The reason we know that conceptually is that when we're finding eigenvectors, this system is going to have non-trivial solutions. Otherwise, we're not going to have any non-trivial eigenvectors. So in order for there to be eigenvectors, which we know that there are, this needs to be a 0. Otherwise, the only solution to this system would just be 0, 0, and that would not lead us to any eigenvectors. So we know, without thinking, that's going to have to be a 0. But let's say we weren't thinking about it conceptually. If we actually trace through the algebra, we'll do it just once so that we can really convince ourselves here. We'd have minus 13, and then we'd have to go minus 1 minus 8i times that entry in the top right. So that would be minus 1 minus 8i over 5. Okay, so let's just try this algebra, see what happens, and just convince ourselves that this is going to be 0. So minus 13 minus, this is all going to be over 5. And so what we'll do here, let's just multiply the 1 minus 8i times the minus 1 minus 8i. Let's just FOIL that out. So we'd have, in brackets, just because of the negative sign here, we'd have negative 1. We'd have minus 8i plus 8i, and then plus 64i squared, which we would call negative 64. Okay, so let's see where we're at. We got minus 13 minus, and then inside the brackets we've got minus 65, and that's over 5. So let's do that. Great, so minus 13, really plus 65 over 5. Well, 65 over 5 is 13, so indeed we do get 0. And that's really the only time we're going to go through that type of long calculation. When we do this for our other eigenspace, let's just understand conceptually that that's going to have to be a 0. If this were any number other than 0, we would have only the trivial solution to this entire system, and that would not lead us to any eigenvectors. So since we know there are eigenvectors, we know this has to be 0. Okay, from there, let's think about solving the system. So we'd have a single parameter, x2 would be t. Usually when we're talking eigenvectors, we're just generically calling our variables x1, x2 here. So x2 equal t, and then let's think about our top row. That would be saying x1 plus minus 1 minus 8i over 5 times x2 equals 0. Okay, we're going to bring this term over to the other side to solve for x1. So x1 equals minus negative 1 minus 8i over 5 x2, if we're being super careful about the signs. And then all those negatives are going to become positive as we multiply through. So we'd say x1 equals 1 plus 8i over 5, and just say x2 is t. That way we're writing everything in terms of our parameter. And then we've got our values for x1 and x2, so we can write up our vector form. So we can say vector x, these are giving us all our eigenvectors. So vector x equals something times t. Putting the correct coefficients in here, it would be 1 plus 8i over 5 and 1. And strictly speaking, you could say for t not equal to 0, because usually you don't consider the 0 vector to be an eigenvector. Great, so that's our list of eigenvectors. I would point out that because of the fraction in here, what's often done is just to scale this vector. Let's multiply it by 5, so we can say 1 plus 8i and 5. And the reason that's valid is that t at the back here is already representing that we're taking all real multiples of this vector. So you're free to scale the vector itself since we're talking about the entire family of multiples of that. So when we write down a basis for our eigenspace, this is the eigenspace associated with 2 plus 8i, so let's write it like that. Then you're just grabbing your vector that's being multiplied by the parameters, so the 1 plus 8i and the 5. So if you had 2 parameters in there, you'd have 2 basis vectors. So that's how we go about finding an eigenspace for a complex eigenvalue. We're going to do the same calculation for the other eigenspace, but do this a little bit faster the second time. So we're now looking at the eigenspace associated with 2 minus 8i this time. I write that down just so we remember which eigenvalue we're working with. So we are going to calculate a minus 2 minus 8i times I, and we're going to solve the homogeneous system there. So our matrix A, remember, looked like 3 minus 13, 5, and 1, and we need to subtract 2 minus 8i from each of those diagonal entries. So we're writing things like 1 minus 2 minus 8i and zeros down the right side. Great, so same kind of idea as before. Actually, it might be smart to simplify the diagonal entries. So let's say 1 plus 8i and then minus 1 plus 8i. Notice these are now plus 8i because of the double negative there. Same idea as before now. We're going to try to get the real number in the upper left just to simplify the algebra. So let's swap rows. There we go. And then we'll divide by 5 in that top row. Make everything nice. So 1 minus 1 plus 8i over 5, and then 0 in the top row. And bottom row can just be recopied. Okay, now skill testing question. Last step of the RREF. Can we do this without making life too painful for ourselves? So formally what we're doing, we're taking row 2 minus 1 plus 8i times row 2. Let's focus in on the bottom row because I'm really excited to do that part. So row 2 minus 1 plus 8i times row 2, that's going to be 0. And this part here also going to have to be a 0 because we know we're going to get eigenvectors here. We know this number that we're working with is an eigenvalue. So we know we're going to have non-trivial solutions to that system. That tells us this is just going to be a 0 row. So there is the RREF, and then we can go through the solution process. So if we call our variables, rather, x1 and x2 here, x2 is going to be t. From the top row, x1 plus negative 1 plus 8i over 5 x2 is going to equal 0. So we're going to bring this term over to the other side, and signs are going to change in the coefficient. So we'll say x1 equals 1 minus 8i over 5 because of the sign change, and the x2 becomes t. So there's our x1, there's our x2. Let's write out our vector form. 1 minus 8i over 5 and 1 times t. And often better to scale that just so you don't have to deal with the fractions. So let's multiply through by 5. We'd say 1 minus 8i 5 times t. Whichever way you write it, you're talking about the same set of vectors because you're already taking all multiples of this vector by putting the t there. So better to say 1 minus 8i 5 times t, and then we can give a basis for our eigenspace just to finish up. So basis for the eigenspace 2 minus 8i, best way to write it down. We've got a single basis vector and it looks like 1 minus 8i 5. Great, so that's all we needed to say about complex numbers.